I'm going to go over the answers to the 7.1 quick check. So the first question on here was, to fill in the blanks, and this is an important statement here about collision theory, and that's that a reaction takes place when the molecules collide with enough energy in the right orientation. Now those three terms kind of relate to the next question when we say, well, state 5 things that can be done to speed up a reaction. So as far as collisions are concerned, if you increase the concentration, that's the way you get more collisions if you're talking about a solution. If you have gases, okay, then increasing the pressure or decreasing the volume would be the same thing, would cause more collisions between the gas particles. And if you're talking about a solid, in like fire or something where you're burning some solids, then the more surface you can get, more surface area, then there's getting more collisions between a solid and, let's say, a gas and all that. Now, as far as the energy is concerned, if you can increase the temperature, then you speed up the particles and you get greater energy of collisions. So they're going to collide harder. They're also going to collide more often, but the colliding harder is the important part. And then the last part of this is that if we're talking about a catalyst, okay, a catalyst allows two things to hit with the right orientation. And that way they don't have to collide quite so hard. That speeds up the reaction. So these 5 things speed up a reaction, and they relate to the 3 parts of the collision theory. Now the potential energy graph, we want to go through and want to label the graph. So the first part is over here. This is the reactance, okay, over here at X. And notice that the line, that kind of swoops up, and that's just, a problem we have with how to draw these curves. It really should be kind of flat. Okay, y is the products, and we're getting this from this equation. X turns into y, so X is the reactants, y is the products. Way up here we have our transition state, okay, which is some kind of an in-between sort of a molecule. Now we want to label some of the other pieces on this, and that would be that the activation energy is the energy it takes to get from the reactants to the transition state, and the activation energy for the reverse reaction would be from here to here. And the delta H would be the energy from the reactants to the products. So in this case, it would be this tiny little arrow here. That's the delta H of reaction. So this would be activation energy in the reverse direction. This would be activation energy in the forward direction. So let's put some numbers in. So we're going to say that the energy of the X, the reactants, okay, you just read that off the graph, it's at negative 80. For Y, again, we read that off the graph, we can see that that's at negative 70. The transition state, okay, for the uncatalyzed reaction, uncat, that's at negative 30. And we have 2 different curves, and the lower curve is always the one with the catalyst, because a catalyst lowers that potential energy, that barrier, and makes the reaction go faster, makes it easier to happen. So that's going to be at negative 60 right here. So if you see 2 lines, the top one here, that is the catalyzed, and the lower one, that's the uncatalyzed. Now some other numbers here. So for the forward reaction, the activation energy is how much it goes from here to the transition state. And if you just kind of look at the graph, we go 10, 20, 30, 40, 50. That's 50 up 50. Okay, with the uncatalyzed, to get from here to the top of the new transition state, that's only 20. Okay, and the delta H is from the reactants to the products. We're going uphill by 10, so that's positive 10. For the reverse reaction, if we're going to say now we're going to go from Y and go back to X, well, the delta H is going to be the same number, only it's going to be negative in this case, because now we're going downhill from Y down to X. Or if you want to do it mathematically, it's final minus initial, so negative 80 minus negative 70. So that's going to be a negative 10. The going over the hills in the reverse direction, so the uncatalyzed, it would be up by 10. So you can see 10, 20, 30, 40 to get up to the transition state. And to get to the catalyzed, you only have to go up by 10. So notice that activation energies are always positive numbers, because we're always going over the hill this direction or going over the hill this direction. Next part here, if we're talking about draw a line that represents the temperature of the sample Okay, temperature of the sample is the average kinetic energy. So temperature equals average kinetic energy. So we just kind of look at our curve. This is our kinetic energy curve. Remember that it's a left and right sort of curve. And we just put a line kind of down here, and that would kind of represent our temperature. So we could get the average kinetic energy be temperature. Now, show what would happen if the temperature were increased. I'll use red for that. So if the temperature were increased, that means this curve is going to be stretched out to the right. So it's not going to be quite so tall because the area under the curve stays constant. And what would happen if we added a catalyst? Okay, I'll do green for catalyst. And a catalyst, it affects the threshold energy. So the threshold energy would be somewhat over to the left. Now, how much over to the left, it doesn't matter. Just the idea that it's going to be somewhat to the left. Now, color in the particles that are going to be reacting under the new conditions. So you want everything past our dotted line under our new curve. So all these particles over here are going to be the ones that are going to be able to react. So all the particles that are past our threshold energy and under our new curve. Now the last part down here has to do with multi-step reactions. So here we have 3 steps. So what's the overall equation? Well, the first thing is to kind of put these 3 equations together. So I like to draw a line over the arrows to keep myself from getting confused. And then we want to cancel out anything that shows up on both sides. So the HOCl shows up on both sides. And it looks like this HC2O4 minus, that shows up on both sides. Now everything else, oh no, here's water. Okay, so water shows up on both sides. And be careful, Cl2 and Cl minus, those are not the same thing. So we can go back and write our equation. So on the left side, I see Cl2. And I see H2C2O4. It's a 4. And it turns into, it looks like 2 Cl2s. And well, we have 2 H pluses. And 2 CO2s. So this is really kind of tiny and slumpy, sorry. So then we have over here what we have, what are intermediates and catalysts? Okay, intermediates and catalysts both would cancel out of our equation. So these blue ones that are formed in one step and then lost in a later step, okay, used up in a later step, those are intermediates. So our intermediates in this case are going to be HOCl, and what else would we do? HC2O4 minus. Sorry, you can't read that. And then our catalyst would be something that is used up right away, but it's reformed at the end. So the catalyst in this case would be H2O. So which is the slow step? Now the slow step we're going to get from this graph over here. And what we need to look at are the activation energies. So to get over this first hill, we're talking about that much activation energy. And to get over the second hill, we're talking about that much activation energy. And to get over the third hill, we need all of that much activation energy. So a small activation energy means it's going to be fast, and a large activation energy means it's going to be slow. So who's the slow step? The slow step is the one associated with this large activation energy, and we're talking about steps 1, step 2, step 3. So at step 3 is the slow step. And we just get that from the graph. So is it exothermic or endothermic? Okay, that's just a matter of looking at the initial concentration, the initial energy and the final energy. And so we are going downhill. Okay, so that's going to give off energy, and we know that that is exothermic. And that is 7.1.